first of all, let's say that I have this piece of copper wire. Okay, so here's the reaction that's occurring in these pictures. You have copper wire reacting with some solution that's got silver ions in it. And what happens is that there's a reaction where the silver takes on electrons, the silver ions get reduced. They take on electrons and become silver metal. So that's what this sort of fluffy stuff that you see forming on the wire, that actually is silver metal. And where are those electrons coming from? You know, in order for these ions, positive ions, to become neutral metal, they have to take on some electrons. Well, the electrons are coming from the oxidation of the copper metal. So this copper wire, some of those atoms, as you can see here, so these copper atoms are becoming copper ions in solution. And so it's providing electrons to those silver ions and causing them to plate out as silver atoms on the surface of that wire. So, and that's what you see happening here. And also notice that the solution is getting blue. The solution is very blue over here. And that's because these copper ions that are in solution, they have that characteristic blue color to them. Okay. All right, so this is just kind of a redox reaction that you can see occurring. All right, now the other thing, and here's another one. In this case, we're putting aluminum foil in a solution of copper ions. So the solution is blue because of the copper ions, and you just dunk some aluminum foil in there. And look what happened to the temperature. So this mixture went from a 20.5 degrees Celsius all the way up to 29 degrees Celsius. And you can see also the copper has formed on the surface of the aluminum. Some of it has fallen off and sits on the bottom. But again, you have this redox reaction, and you know that it's releasing energy because the temperature went up, right? It went from 20.5 all the way up to 29 degrees. So that reaction is heating up the water. And that's the other thing that we can use when we have these redox reactions occurring. And so, for example, you know, a battery, that's what's going on in a battery, like a AA battery. You have a chemical reaction, a redox reaction, and you're exploiting that reaction to get energy out of it. Right. In this case, the energy is going to heating the water. In the case of a AA battery, it's used to, you know, run some sort of electronic device like a remote control or like a wall clock or something like that. Okay, so that movement of electrons has energy with it. And the terminology for that is current. That's what we could just like, you know, the current of a river. Well, you can think of like a river of electrons has a certain current, right? So the movement of electrons creates a current that can run a motor or a light bulb or something like that. And any chemical reaction that creates this current, these are called voltaic cells, or another word for it is galvanic cells. Those words are used interchangeably, really. So anytime you have a redox reaction, a setup where you have this redox reaction that generates a current, okay, generates the flow of electrons, that is a voltaic cell or a galvanic cell. And that's what we're going to get into more in lesson 2. Okay. Well, the other thing, though, is that you can go in the opposite direction. Instead of having a chemical reaction that creates a current, you can use current, or you can use electricity to cause chemical change, to cause a chemical reaction. And so one example of that would be, I don't know why, but this is messed up. I'll fix that later, but this should say 2H2O. There should be an O there. Okay. So I guess I'll draw a little O there. I don't know where that went. H2O, and that should have an O there. Somehow all my O's got deleted. This should be an O. Oh no, wait, never mind that. You know what? I'm just going to erase all those. I'll fix that later. But this should be 2H2s, and this would be a gas. Okay, and that's an O2 gas. I'll have to figure out why that happened. But in this case, what we're doing is we're using electricity. We're applying a voltage, okay, and it's breaking water apart into gases. And what we're going to start off with is learning how to balance redox reactions. Okay, it's not as simple as, it's got some unique things to it. Back in Chem 1, we learned how to balance chemical reactions, and we're going to employ those skills, but we have some other things that we have to take into account when we're balancing redox reactions. Okay, so, and I throw this up there, first of all, because it's already in the handout, but also because it's a reminder to me to let you know that, you know, I don't necessarily expect you to memorize this list of steps. I will give them to you on the quiz and on the final, if there are any questions that involve balancing redox reactions. Okay, so, but assigning oxidation numbers, what we went over in lesson 1, it's very important. That's where you start, because that enables you to do step 2, where once you get everything into oxidation numbers, then you can see what your oxidation process is and your reduction process. And so you want to divide that reaction up into the oxidation half reaction and the reduction half reaction. And then you're going to balance all of the elements, okay? And you start just by balancing all the elements except oxygen or hydrogen. And that's because there are special rules for balancing oxygen and hydrogen. You're going to balance oxygen by adding water. Then you're going to balance hydrogen by adding H+. And then you'll balance charge by adding in the electrons. And if you're you put the electrons on the right, the product side, for the oxidation half reaction, and you put the electrons on the left, the reactant side, for the reduction half reaction. Okay, now this is just to be complete, but if you're in basic solution, you would do that differently. But I'm not going to give you any. I'm not going to give you any to balance that have basic solutions. And so now, once you get the balanced half reactions, then you just have to reconcile the number of electrons for each, because as we already said, the number of electrons transferred in the oxidation has to be the same as the number of electrons transferred in the reduction. So that's what step 4 is all about. And so then you do step 5, which is you just add the half reactions together, and then you just clean it up by deleting things or canceling out things that are on both sides. And if you can reduce the coefficients down to simpler or to lower numbers, then you do that. All right, now I know that that is just kind of meaningless, just going through all those steps. The way in which you really learn it is by seeing some examples and doing some on your own. So that's where we'll start. So we'll start with an easy one, and then we'll make it more challenging. So we just want to balance this unbalanced redox reaction. Now, the first question is, well, how do you even know that it's unbalanced? It looks pretty balanced. I got one iron, one aluminum, one aluminum. So on the surface, it looks like it's balanced, but it is not. And so the way in which you can tell is because there's not charge balance. Remember from Chem 1 that you not only balance the atoms, but you also have to balance the charge. And in this reaction, I've got a +2 charge on the left, but I have +3 charge on the right. So the charge is not balanced. So that's what gives it away. All right, so now we got to deal with that. So first of all, we assign oxidation numbers. That's step 1. So remember that for a monatomic ion, the oxidation number is just the same as the charge. And for a pure element, the oxidation number is 0. Pure element, 0. +3 charge, +3 charge. So now that I've assigned the oxidation numbers, I can identify the oxidation half reaction and the reduction half reaction. Okay, so the aluminum increased its oxidation number. It went from 0 to +3. So that's the oxidation half reaction right there. Now the iron +2 ions, iron +2, that underwent reduction because it went down. It went from +2 down to 0. So that, the iron +2 becoming iron metal, is the reduction half reaction. Okay, so now I just break that up into the different half reactions. So I said the oxidation half reaction was the aluminum becoming the aluminum +3. Aluminum becoming aluminum +3. And the reduction was the iron +2 becoming iron. Iron +2 becoming iron. Now you'll see why I left some space there in just a second. Okay, so the next thing I need to do is to balance charge, and you do that with electrons. I can't remember what number we're on, but we're just going through the step-by-steps. I didn't have to add waters or H pluses because I was balanced in terms of oxygen and hydrogen because I don't have any oxygen or hydrogen anywhere. But we'll get to that in the next example. But I do have to balance charge. So I'm at the step where I'm balancing charge, and you do that with electrons. Now, for oxidation, remember what oxidation is. Oxidation is losing, oil rig. So this aluminum is losing 3 electrons. Electrons will be a product of oxidation. And that also balances my charge. 3 electrons, that's 3 negatives, will cancel out these 3 positives to make it overall neutral on the right. And I need that because I have overall neutral on the left. Okay, so that's why I put 3 electrons on the product side. So now I've got to put some electrons on the reactant side for the reduction half reaction. Reduction is gaining. So this is going to gain some electrons to become iron metal. So it's 2 electrons. And again, why is it 2? Well, I've got to cancel out these 2 positive charges, so to do that with 2 negative charges to get overall neutral. All right. So I've got my oxidation half reaction. I've got my reduction half reaction. But now I need to do something to reconcile the number of electrons transferred in these processes. So, in the oxidation half reaction, I had 3 electrons released. In the reduction half reactions, I had 2 electrons gained. Okay, so that's different, 3 versus 2. So I have to reconcile that. So what do those, what is a common multiple, or a common multiple of 3 and 2? Well, it's 6. So I just need to make this an overall 6 electron process. And I do that by multiplying this half reaction by 2. Because 2 times 3 electrons is going to be 6 electrons. And so now I multiply this half reaction by 3 to make it a 6 electron process. So 3 times these 2 electrons give me 6 electrons. So now I have 6 electrons being released in the oxidation half reaction. And I have 6 electrons being gained in the reduction half reaction. So, and these multipliers apply to everything. So that 2 multiplies times that, and it multiplies times that, and it multiplies times that. And the same thing with the 3. So then the next step is to add these 2 reactions together with, I'm taking into account all the multipliers. So I've got 2 aluminum atoms. And then over here, I've got 3 times the iron plus 2 ion, 3 times the iron plus 2 ion, 3 times the 2 electrons means 6 electrons. Okay, and so then on the product side, I've got 2 times the aluminum plus 3, 2 times the aluminum plus 3, 3 times the, 3 times the iron metal, 3 times the iron metal, and I skipped this, sorry. So 2 times the 3 electrons is 6 electrons, 2 times the 3 electrons is 6 electrons. So I've got 6 electrons on each side, so they can cancel out, okay? So now the net balanced equation is just everything that's left over, okay? All right, so that's how you balance these kind of reactions. Okay. Now, believe it or not, that was a fairly simple example. So now we'll do a more challenging example. And you'll see why this one is more challenging once we get to the balancing the oxygens and the hydrogens, okay? But you start off the same way. You got to assign oxidation numbers to everything. So here are my oxidation numbers. So this manganese is actually a +7 right here, okay? How do I know that? Well, oxygen is -2. I can hang my hat on that, and there's 4 of them. So 4 times -2 is -8. I need to keep one of those negatives, but I need to cancel out the other 7. So that's why the manganese must be a +7. Because +7 -8 gives me a -1 overall. Okay, this is monatomic, so the oxidation number is the same as the charge. This is monatomic, so the oxidation number is the same as the charge. This is a pure element, so its oxidation number is 0. Okay, so once I get the oxidation numbers, I can identify my oxidation half reaction and my reduction half reaction. So this decreased from +7 to +2. Okay. And then this is oxidized because it goes up from -1 to 0. Okay, so my oxidation half reaction is going from the bromide ion to the bromine compound, or not compound, the element bromine, Br2. And so that's why I have to have this 2 out in front, because I know that in order to keep my number of atoms balanced, I've got 2 bromines on the right, so I'm going to need 2 bromines on the left. So that's why I had to throw that 2 in there. Okay, so that's my oxidation half reaction. So my reduction half reaction is going to look like this. And remember, I'm going to leave some space because this is where I'm going to put some electrons and other things to balance stuff out. But it goes from a +7 to a +2. Okay, so this is my reduction half reaction. It went down from +7 to +2. So that's my reduction half reaction. +7 to +2. Okay. So now I've got it divided up into my oxidation half reaction and my reduction half reaction. So, and I've already balanced all of the elements except oxygen and hydrogen. We've got 2 bromines, 2 bromines, 1 manganese, 1 manganese. So now I have to balance oxygen and hydrogen. So how do you do that? Well, look at the step. It says for every oxygen, we need to add a water on the other side. Okay. So that's why I add 4 waters to this side, because that gives me the 4 oxygens. 4 oxygens, all right? But now I've got hydrogen over here, no hydrogen over here. So I'm going to put H pluses over here to balance the hydrogen. So I've got 4 times 2, so that's 8 hydrogens. So now I've got to put 8 H pluses over here. Okay, so that's why I put that there. So plus H hydrogen ions. Okay, so now I've got one manganese, four oxygens, eight hydrogens, but I'm still not balanced in terms of charge. This is where you got to do a little bit more math than perhaps you like. But over here, it's easier if you look at this one just at the right side first. Over here, I've got a +2 charge overall. We got +2 charge on that, neutral charge on that. So over here, I've got +2. Okay, so I got to make this side +2. Well, right now I've got 8 times +1, so that's +8. And I've got a -1. So +8 minus 1 is +7. So I've got right here, I've got +7, but I need to bring that down to +2 because you have to have charge balance. And remember, this is a reduction process, so I also expect that I'm going to have to add some electrons over here. Reduction is gaining. Okay, so I'm going to add enough electrons to this side to balance out my charge. Okay, over here, I should have done this one first. I'm sorry. So here we had 2 negatives, so I can balance that by putting 2 negatives over here. And oxidation is losing, oil rig. So I put my 2 electrons here to balance out my charge with this side. So 2 negatives, so now I have 2 negatives. And also the electrons go on the product side because this is oxidation. Oxidation is losing. So these guys become bromine, Br2, and release 2 electrons. Okay, now I was focused so much on the reduction half reaction, I forgot all about that one. This one is 5 electrons on the reactant side. So now again, if you look at your charges, I've got 1 negative plus 5 more negatives, 6 negatives, plus 8 positives gives me overall +2. Well, over here I've got +2. Okay, so now my charges are balanced on each of these. Okay, but I have different number of electrons involved in each. So this only had 2 electrons involved. This one had 5 electrons involved. So I have to make them the same. Well, what's your common multiple? In this case, it's 10. So I'm going to multiply this top half reaction by 5 to get 10 electrons. And this one I'm going to multiply by 2 to get 10 electrons, so that I have 10 electrons released, and I have 2 times 5 electrons gained. Okay. So now I just add everything together, and don't forget to multiply everything out. Okay, so 5 times 2 is 10 bromides, and then I've got the 2 times the permanganate, so 2 permanganates. I've got 2 times the 5 electrons is 10 electrons. I've got 2 times the 8 H pluses for 16 H pluses. And then on the product side, I've got 5 times the bromine, so 5 Br2s. I got 5 times the 2 electrons, so 10 electrons. I've got 2 times the manganese +2 ion right there, and then 2 times the 4 waters to give me 8 waters. And so now you just cancel out everything that you can. And in this case, that's just the 10 electrons. So you got 10 electrons in each side, so they cancel out. All right, so that gives you the net balanced chemical reaction of this right here. Okay, and once again, if possible, you should simplify it. In this case, I can't, but if I could divide all of these coefficients by some number, you should do that too. All right, so like I said, that's a little bit more challenging. And just always make sure you can, do your balance of atoms on the left and on the right, do your balance of charge on the left and on the right, just to make sure. And in this case, we'll start with a simple one. So we've got the silver ion reacting with cadmium metal to form silver metal and cadmium ions. And once again, you know that it's not balanced because you got +1. It's not balanced in terms of charge. You got +1 on the left, but +2 on the right. So assign oxidation numbers, +1, 0, 0, +2. So that identifies your oxidation process, goes from 0 to +2. And your reduction process goes from +1 down to 0. So you break it apart into your oxidation half reaction, cadmium becoming cadmium +2, and your reduction half reaction, your silver becoming silver metal. Now in this case, we are already balanced in terms of atoms. I've got 1 cadmium, 1 silver, but I'm not balanced in terms of charge. So I do that with electrons. I'm going to add electrons on the product side for the oxidation half reaction. I add electrons to the reactant side for the reduction half reaction. Okay, so this requires 2 electrons to cancel out these 2 positive charges to give us overall neutral on the right, because I have overall neutral on the left. And in this case, I just need 1 electron on the left side, on the reactant side, +1, minus 1 gives you neutral, neutral over here, okay? But I got to reconcile the number of electrons that are transferred. In this case, I had 2 electrons transferred. Here I only have 1, so I multiply the whole thing by 2. Okay, so then I just add everything together, cancel out what's on both sides to get the net balanced equation. So the cadmium metal reacts with 2 silver plus 1 ions to give cadmium, 2 plus ions, and 2 silver metals. All right. So in this case, I only have really, it's just a half reaction. So I just have I only have to do it for the oxidation because it's going from titanium 0 to titanium plus 2, all right? And remember how to balance the oxygen is you put water on the other side, 1 water for each oxygen. So since I had 2 oxygens over here, then I put 2 waters over here. So now I'm balanced in terms of titanium, 1 titanium, 1 titanium, 2 oxygens, 2 oxygens. But now I balance the hydrogens by adding hydrogen, or H plus, to the side that needs it, okay? So I have 4 hydrogens on the product side, so I put 4 H pluses on the reactant side, okay? So now I'm balanced in terms of all my atoms, but now I just need to balance charge. So I've got a total of plus 4 charge on the left, but I've only got plus 2 charge on the right, okay? So did I say this is actually a reduction half reaction? This is not an oxidation half reaction. So I got to add 2 electrons to the reactant side. Okay, so I got 4 pluses and 2 minuses to give me overall a plus 2. And I've got 2 pluses and a water, so that's neutral, right? So that's an overall plus 2 on this side. Okay, and so that means you're done. All right, so and let me go back to how I knew this was a reduction half reaction. I probably should have said that at the beginning. But if you look at the oxidation number here on this titanium, it's plus 4, whereas the oxidation number on this titanium is plus 2. Okay, so since it went from plus 4 to plus 2, that way I know it was reduction because it went down from plus 4 to plus 2.